Yeah, so where we are. So our main
আমরা কিন্তু আপনার কথা এত শুনতে পাইনি স্যার।
I didn't speak anything, so I have just started now. I have to update some settings. Okay, so I think now I'm audible and you can see my screen. So that I'm talking about that models of computation. So main components of it that is called CPU or the central processing units. And based on the problem level, sometimes we need to interact with another components and that is called memory. So this is the major components we have. Now let's try to complete our whole components. So as we know, main part that is the processing unit, its jobs to compute all the things, all the problems, but it needs also input to process the data. At the same time, it needs the output. So these are the another level of components that is called the IO components. And we divide our memory into two parts. One is program memory and another is temporary memory. So this is our total diagram of model of computation where we have basically three components. First one is the central processing unit. Second one is the memory. So we divided them into two parts. One is program memory, another is temporary memory. And finally, we have the IO devices where basically we pass the input and also get the output. So this is the basic diagram or components we have. Now let's try to get the intuition first that why this is actually why there is a connection from our courses. Look, there is example problem. Let's say f of x equal to x cube. So a example problem is given and see program memory already has the ability. There is a box. I think you noticed that there is a box under the program memory where compute x multiply x and again compute x square multiply x. This algorithm is showing or the solution how this function can be solved. Their intuition, their computation is given. So program memory is responsible for how your problem can be solved. Those prototype will be there. And right now, we actually differentiate our CPU to the program memory, but later on, we will see that this program memory resides in the CPU. But for the first phase, uh, we understand that program memory is the part of the CPU and where the solution or the how the problem can be solved, that computation is resides in the program memory. So, and this topic is also important that I should, mention that from this model of computation part, this topic is very important for your midterm exam at the same time. So, how you will solve a simple problem? I'm just uh, I'm just giving the answers. These discussions will be the answers for your solution for your problem. So let's say one problem is given. So after this discussion, after this lecture, I will give one similar problems so that you got the idea. So and you need to draw four picture. So this is the first picture. This slide is the first picture where you got the function, and based on the function in program memory, you will write the how the function can be computed. So computation you will write. Now our next part. So this is the next figure. The second figure. This is the second figure where you will write the input. I mean, if your input for one variable or two variable, whatever it is, you will take the input in the second figure. So this is your second figure. Okay, so there will be four figure. And sometimes what I found that students for the short amount of time, they draw it only for once. So what happened, you will get the half of the marks. So remember, you need to draw it step by step. I mean, you need to draw the four figures separately. So this is our second figure, where you must mention what is your x value, or what is the input you will provide it. Next part, we will do the calculation in the temporary memory, because based on the program memory, based on the solution, we will actually apply our computation with the x value. So if we try to I mean, understand this computation, look, computation's just saying that we need to compute x multiply x, and then we need to compute x square multiply x. So these steps will be just repeated with the value of x equals to 2. So 2 into 2 equals to 4. 4 is stored in z. And finally, z is multiplied by again x. That is actually 8. Ultimately, f of x equals to 8. So this is the third figure, third diagram. Now this is a fourth figure, where you will actually show the output, that what will be the output of this. So in this fourth step, you will solve this problem. I know there is a question behind that, behind these types of solution, that why we need to actually draw these four types. Basically, to understand that step by step, uh, our problems are solved using different components. So to get the better intuition, you will do that. Now, so I am repeating the solution again. So after the class, you will solve this problem. So what you need to do, I am again repeating. So very first, when you get the function, you will complete this whole diagram, including the program memory part for your function. In the second figure, you will complete the input section part. In the third figure, you will complete the temporary memory part, I mean the whole diagram. And the fourth figure, you will draw these complete things. Okay, so every time, just each of the step will be filled, but others will remain completely same. I think you got this. So let's back to the automaton. Just now try to understand why. I think now you will get the better idea why we actually solve that problem based on this. Remember the program memory. I already told that program memory is actually, I mean, it's a part of the CPU. So CPU and the program memory, this is actually inside a box, and this box is called automaton. That we are talking about automata, or the machine, or the processor, or the system, what actually define it. But ultimately, CPU plus program memory, both combinedly called automaton. And other components actually will be there, like temporary memory, input and output. So what basically we have seen in the CPU and program memory, that is basically these things. That means we actually label them using CPU, or we label them using program memory, but ultimately under the hood they are nothing but some transition with the state. So the circle that we actually mentioning here, and the transition here, that is called actually, the circle is defined through the states, and the red arrow marks is actually defining the transition. So that is called the I mean, state diagram transition. So under the hood, these are the transitions, these are the things that is capable to solve any problem. Any problem means the range of problems we know. That is, I'm mentioning that any problem. So in this CPU and program memory, we actually put all the solvable problems model, and rather on we actually pass input, pass out, pass input, and calculation is possible through the program. But if this sort of transition is not will be there, our machine cannot solve that sorts of problems. So I think uh, you now got this, that um, what is actually called stated transition. We will discuss it later because we will design them ultimately. That is our part. But now you must understand that what basically we are going to design. So this is called the automaton, and on top of they are known as CPU plus program memory. So, and automaton is nothing but some state with transition. So we will actually understand them later on. Now we need to get the idea of different kinds of automata. So automata are distinguished by the temporary memory basically. So if you see the temporary memory here, so based on this temporary memory, your automata is differentiated, or we can categorize them. So let's understand the finite automata. So no temporary memory is there. That means this temporary memory is absent in the finite automata. In pushdown automata, one memory is used that is called stack. And Turing machines, random access memory is used. I think you know from it first class. But so if we understand, if we try to understand our finite automaton with a diagram, I think this is this is the best diagram to understand them. Now we don't have any CPU, we don't have any program memory. Rather, we are showing it with some transition with states. So this is called the finite automaton. And clearly we have seen that there is no temporary memory. So only input and output is there, and the machine is there. So there is some examples that, let's say, elevators and vending machines, right? Right now, everyone is familiar with the vending machine because in metro rail, most of have you used this vending machine. So elevators, vending machine, automated door, these are the examples of this finite automaton, or we can call them small computing machine or small computing devices. Let's go for the push down automaton. So I think we have now temporary memory, and we know that stack where we have the push and pop operation. So now this automaton actually is reliable on the temporary memory, I mean stack, and similar things happening. So example for push down automaton, let's say compilers for programming languages. So medium computing power. And maybe in the last class, I showed a simple example how stick can help us to detect syntax error in the for loop, or even if else, whatever it is. And the last one is the Turing machine. So regarding the Turing machine, we have random access. We have random access memory, RAM, and any sorts of algorithm can be solved using Turing machine, and that is the highest computing power we have. Okay. So I think you got the idea right now that what is actually automaton called, and what is and where this automaton actually resides on, right? So and why? Look, I mean these models. I mean they are not only research in the computer. If you just imagine this as a computer, it's not like this. This simple CPU, I mean, this automaton input and output and memory can be resides on your, I mean, smartphone, can be resides on your calculator, can be resides on your, I mean, smartwatch, can be resides on your headphone, can be resides on your any electrical devices. Okay, so I mean, just for the CPU, you should not, I mean, assume that this is for the computer. Everything's actually is a computer because every devices can calculate it, right? So these are the machines, these are the I mean core functionality, core thing that actually make a machine able to solve a specific purpose. So here, I think from my last class discussion and today's discussion, you should get this, that the power of automata actually. So let's say simple problems that can be solved by the finite automata. So we can actually call finite automata a less power model. At the same time, more complex problem, push-down automata. So, I mean, medium power full model it, and the hard problems that can be solved by the Turing machine, and we can actually call it a more powerful machine. That means solve more computational problems. So this is actually the, I mean, range or level of problem versus model. So there can be one
স্যার,
simple question. Yeah, sure.
এখানে তো দেখতেছি যে মোর কমপ্লেক্স আর হার্ডেস্ট। তো মোর কমপ্লেক্স আর হার্ডেস্টের মধ্যে মানে ডিফারেন্স, মানে এটা কেমন বোঝাইতেছে? একটা টিউরিং মেশিন আর একটা পুইডন, এটা একটু জাস্ট একটু যদি বলতেন, মানে একটা হার্ডেস্ট আর একটা মোর কমপ্লেক্স, এটার ডিফারেন্স।
I mean, more complex is compared to the simple problems, and hardest means those problem can be solved, but depending on time, right? So some problems needs a polynomial time, and some problems need NP time, non-polynomial time. So it's just comparing the problem level, right? So more complex problem means rather than simple problems, and hardest problem means of course more than complex problems, but they can be solved based on the time. I mean, time is important there, so they can be solved in polynomial time, and some problems can be solved in non-polynomial time.
আন্ডারস্টুড স্যার। ও, টোটালি বেসড অন টাইম, রাইট?
Yeah, hardest problems are based on that.
ইয়েস স্যার, ইয়েস স্যার, ওকে, থ্যাংক ইউ।
So there is a question that is Turing machine is the most powerful computational model known. So one question, that are there computational problems that a Turing machine cannot solve? What should be the answer?
So maybe yes, sir.
ইয়েস স্যার।
Of course, yes, because unsolvable problems are there, right? I mean, outer box. Can you remember the last class that I have showed a diagram? Outer box, that problems already resides, they are unsolvable. They cannot be solved by the Turing machine. And yeah, so I think we are in the last slide to understand the complexity of the computational problem. So two terms, just we need to understand, we will not go that much far in this topic. One is NP complete problems, another is P problems. So I will start from the P problems. So last time you have seen the tractable problems and decidable problems and there. So P problems means solved in polynomial time. I mean, for a certain amount of time, the problem can be solved. But NP complete problems believed to take exponential time to be solved. That means, I mean, a large amount of time needs to solve to that much of problem, that kinds of problem. So you can just consider one problem, let's say a sorting problem, or let's say a read and write operation problem. It can, if it is very simple, then it may be you can solve this problem less than 1 seconds or 2 seconds, or maybe let's say 1 minutes. But let's say you want to decode a password, and decode a password means, last time I show you that for in cryptography how complex it is important. So in that cases, when you need to find the pattern of a pin of a password, that cannot be solved in polynomial time, that needs NP complete problems, because in every time you need to brute forcefully traverse all parameters, and that must take a, I mean, exponential time to be solved. So these are the basic idea regarding the NP complete problems and P problems. So we are done for today, but you have a task to submit. That is, I told you when I started my class this problem. So show in diagram the execution of a function like f of x equal to x cube plus 2x in a model of computation. So what basically you do, you will draw the first figure, then this whole second figure, then this whole third figure, and then the fourth, finally this figure. So you will take one single page and you will split your page into four parts. So you will actually draw each figure, first part, second part, third part, and fourth part, and submit it, and take the snapshot or take the photo and submit it in your WhatsApp group. And I will request our seer to submit the list of ID who have submitted uh, before 2:30, 3:30. Okay, so our class will end at 2:15. So you will get extra 15 minutes to complete your task. So by this time you will actually complete your task. Okay, I think someone should take the snapshot of this problem and share in the WhatsApp, because I am going to close.
স্যার এটা যদি এক ফিগারে পাশাপাশি লিখে যদি সাবমিট দিই হোয়াটসঅ্যাপ গ্রুপে হবে না স্যার?
You will get, I mean, half of the marks. So you need to draw four figures separately. I already mentioned in the when I am discussing that students
ওকে
sometimes
স্যার।
do that, but you will get the 4 marks.